Slope of a line is just a measurement of how steep that line is. This line is rather steep, and this line not so steep. On this line, to get from one point to another, we go up 3 and over 1. We say the slope of this line is 3. On this line, to get from one point to another, we go up 1 and over 2. The slope of this line is 1/2. This steep line had a slope of 3, and this not so steep line had a slope of only 1/2. A line has a constant slope. Anywhere on this line, you would go up 3 and over 1 to get to another point. Likewise, anywhere on this line, you would go up 1 and over 2 to get to another point. But what if we wanted to talk about the slope of a curve? Perhaps you can see that a curve does not have a constant slope. Down here, this curve is quite steep, whereas up here, this curve is not so steep. We define the slope of a curve at a given point as how steep the tangent line drawn to the curve there is. A line tangent to a curve at a given point is a line that only touches the curve at just that one point. The line tangent to this curve at this point would look something like this. It may be hard to tell, but it's only touching the curve at this one point. And I may point out that there's only one correct way to draw a line tangent to a curve. If I made this line too steep, you could see it would touch the curve in 2 places. Likewise, if it was not steep enough, it would touch the curve in 2 places. So notice the slope of this blue line. To get from one point to another, I go up 3 and over 5. Up 3 and over 5. I'm going to say that this curve has a slope of 3/5 at this point. Let me try drawing a tangent line at this point. It's only touching the curve at this one point, and to get from one point on that line to another, I would go up 1 and over 5. I'm going to say that the curve has a slope of 1/5 at that point. Finally, let me draw a line tangent to the curve at this point. The curve is much steeper here, so the tangent line is much steeper. On that tangent line, to get from one point to another, I go up 3 over 1. I'm going to say that the slope of the curve there is 3. The slope of the curve at this point is only 1/5. The slope of the curve at this point is 3/5, and the slope of the curve here is 3. Here I have a function x squared minus 4x minus 2, which I know is a parabola. It's not linear, it's curved, and we're asked to determine the slope at various points. Let's see what the graphing calculator can do in this situation. Let's take a look at the graph of x squared minus 4x minus 2. I'm first being asked to determine the slope when x equals 3. Well, let's first of all just see where that is. Let me trace 3. So I want to determine the slope of the parabola at this point, 3, negative 5. I want to draw a line tangent to the parabola at this point, 3, negative 5. We're going to use the draw feature. Second, draw. And I want to draw a tangent line. And I want to draw it when x equals 3. So notice the calculator drew a tangent line at that point 3, negative 5, and it's even telling us the equation of this tangent line. The equation of that tangent line is 2x minus 11, which has a slope of 2. The tangent line has a slope of 2, so this function at that point has a slope of 2. Let me clear that line out. Second, draw, and I want to clear my drawing. Let's see what the slope of this parabola is when x equals 2. Let's first see where we are. We want to get the slope at the very bottom of the parabola here at the point 2, negative 6. Let me draw a line tangent to the graph where x equals 2. Second, draw, and I want to draw a tangent line. And I want to do that when x equals 2. The equation of this tangent line is 0x minus 6. The slope is 0. The slope of the parabola at the vertex down here is 0. Finally, we want to determine the slope when x equals negative 1. Let me trace negative 1 just to see where that point is. Looks like it's up here at the point negative 1, 3. Let me draw a tangent line at this point. Second, draw tangent line when x equals negative 1. The equation of this tangent line is y equals negative 6x minus 3, which has a slope of negative 6. So I'm going to say the parabola has a slope of negative 6 when x equals negative 1. Let's take a look at another one. Let's see what this function looks like on our graphing calculator. And we once again have a curve. The slope is different everywhere. Let's determine the slope when x equals 4. Before we do that, let's just see where that is on the graph. We want to get the slope right here at this point 4, comma negative 5.25. So I'll second draw a tangent line when x equals 4. The equation of that tangent line is y equals 2.75x minus 16.25. The slope of that line is 2.75, which means the slope of the curve there is 2.75. And that makes sense. The slope is positive. The graph is going uphill at that point. Let's determine the slope when x equals 2. Let's see where that is on the graph. We're talking about this point right here, 2 comma negative 3.75. Let's draw a tangent line when x equals 2. Looks like the slope is negative 3.2499999, or I'm going to say the slope is negative 3.25. And once again, that makes sense. The slope is negative because the graph is going downhill at that point. Where does the slope equal 0? Well, here the slope is negative, and over here we saw the slope was positive. When the graph is going downhill, the slope is negative. When the graph is going uphill, the slope is positive. The slope will be 0 at this relative minimum point. Let me calculate the relative minimum. This makes a good left bound, and I'll push over here to get a good right bound. And at this point, 3.3 comma negative 6.2, that's where the slope is 0. I'm going to say approximately when x equals 3.3. The slope is also going to equal 0 up at this relative maximum. Let's calculate the relative maximum. I'll come up here and get a left bound on the left side, and then go over and get a right bound. The slope is also going to equal 0 at this point, where x is negative 1.3. When the graph is going uphill, it has a positive slope. When the graph is going downhill, it has a negative slope, but at the relative maximum and relative minimum, it's neither going up nor down. Here's a sketch of the graph y equals x squared. Can we determine the slope of this function at this point without the assistance of a calculator? We should be able to. After all, Isaac Newton invented calculus long before the invention of the calculator. But there's no doubt it's not easy. Let me try drawing a line tangent to the graph at this point. I'm not 100% sure I drew my line correctly, but even if I did, it's going to be very difficult to calculate the slope of this line because the only point I know with certainty that it goes through is this point 1, 1. It would be much easier to calculate the slope of this line because I know it goes through the point 1, 1 and 3, 9. If I know 2 points on the line, I can use the slope formula to calculate the slope. The slope of this line would be 9 minus 1 over 3 minus 1, or 8 divided by 2, which equals 4. Likewise, it would be easy to calculate the slope of a line like this. It goes to the point 1, 1 and 2, 4. It's much easier to calculate the slope on a line like this because we know 2 points. We can use our formula for slope. 4 minus 1 over 2 minus 1, 3 divided by 1 is 3. But we were trying to calculate the slope of this line, and the only point we know with certainty that it goes through is 1, 1. My slope formula doesn't work as well when I only know 1 point. 1 minus 1 over 1 minus 1 is 0 over 0, or undefined. Now, it appears the tangent line I drew goes through these points, which means the slope of this line would be 2. We'll come back in a few minutes and confirm whether or not that's correct. We're going to use this picture to derive a formula that we can use to calculate the slope of any curve. Let me first attempt to name these 2 points I have on the curve. To get to this point, I'm going to go to the right a distance of x. And to get to this point, I'm going to go to the right all of this distance, which I'm going to call x plus h. And I'm going to call this height f of x. For instance, if this distance were 2, I would get this height by plugging 2 into the function. It would be f of 2. If this distance were 3, I would get the height by plugging 3 into the function. It would be f of 3. Well, this distance is x, so the height is f of x. And this height over here would, of course, be f of x plus h. For right now, I'm going to draw a line that goes through both of these points. And writing an equation for the slope of this line should be simple because I have 2 points to work with. The slope of a line is, of course, y2 minus y1 over x2 minus x1. So my numerator is f of x plus h minus f of x, and my denominator is x plus h minus x. And perhaps you see the denominator, this positive x and negative x cancel out. The denominator is simply h. But of course, we're not interested in calculating the slope of a line that crosses the curve at 2 points. We want the slope of the line that's tangent to the graph at 1 point. So what we want to do is imagine the line we would get if we took this point here and moved it closer and closer and closer and closer to this point. We want to find the limit as this distance of h approaches 0. If we evaluated the limit as h approaches 0 of this difference quotient, we would get the slope of the curve at this point. This limit as h approaches 0 of f of x plus h minus f of x over h is what we call the derivative in calculus. We can use that to create a formula to get the slope of any curve.